So, good afternoon, everybody. First of all, I'd like to thank the organization for this opportunity to make this presentation here today, as well as everybody who's watching, be it in place there or online. Thank you to everyone. So today I'm going to talk a little bit about the future of environmental remediation, innovative automation and bioremediation solutions for remote areas. So my name is Eduardo Querido. I am operational manager here at Finkler Sustainable Technology. Brief introduction to our company. We're a company that offers comprehensive technical and legal support directed at various segments, including compliance, management, monitoring, sustainability, and environmental conservation. We have over 20 years of experience in this area, and we currently have a multidisciplinary and experienced team with over 50 direct employees and 30 indirect ones. So this presentation I'm going to make today is not about a specific case, but it incorporates a compilation of different aspects of our experience, like bench tests, field tests, pilots, and remediation initiatives. I will present a composition of our solutions that we have established as an ideal format for optimization of remediation in remote areas. And we talk about remote areas because remote areas represent a specific type of remediation challenges. I know this situation is may not be common to other countries and other contexts, but here in Brazil, it's very common for us to have a contaminated site that is placed hundreds of kilometers from any kind of infrastructure. So this leads to exceptional challenges, and our main challenges are usually lack of access to any sort of connection to the power grid and poorly maintained access or even non-existent access roads. And all these logistical challenges contribute to an increase in remediation costs. Now, every time we head to the field, we have a well-established and technically based field plan. But it's very common for field conditions to demand specific changes or adaptations. Now, in this sort of context, traditional remediation systems require intensive physical presence to enable these specific adjustments. So monitoring and automation, as well as the incorporation of different remediation techniques, can help us optimize the remediation efforts. I know that these aspects are important to all remediation sites, but specifically for remote areas, they have a larger operational and financial impact. So what are the key factors of our implemented system? Well, automation is a key factor in remote areas. It enables us to continuously operate without having to have a physical presence in the site. It also enables optimized pump performance and can remotely adapt to some extent to changing site conditions in real time. We also implement solar power with auxiliary power generators. This enables us to have a power supply flexibility. Now, the specific capacity of each component will vary according to site specifications. Factors like predicted operation period, distance to resources are taken into account for us to balance implementation efforts and operational optimization. In this sort of context, reduced footprint is also very important, as this reduced footprint will help us reduce the implementation time and costs. Finally, the system that is projected has to be designed to withstand harsh environmental conditions. We often encounter high volumes of rain, elevated temperatures, and high incidence of atmospheric discharges. So in this context, a robust, well-designed system will help us minimize the maintenance requirements. In this sort of project, surveillance, cameras, and satellite connection must be applied. The cameras enhance security and provide site conditioning monitoring, and satellite connection enables reliable communication and control, which are utmost requirements for remote operation. So we apply a series of sensors to support these remote operations. We use water level sensors to monitor groundwater and tank levels. This enables us to do pump adjustments and avoid shutdowns and damages. We utilize gas sensors that allow us for safe operation and regulational compliance. We use flow and vacuum sensors, which enables adjustments to maintain optimal pump performance and consistent remediation performance. These sensors also detect potential leaks and blockages within our lines. Finally, volume monitoring provides a progress evaluation and can potentially provide data for reinjection planning. So in this kind of context, reinjection is a technique that is very important to reduce the movement, the transportation, and the destination of the effluent that is removed. But it presents specific challenges. It must be done very carefully. Pressure and flow rates must be rigorously controlled to prevent uneven flow distribution and formation damage. Now, there are two main ways we can reinject this effluent. We can do it through a natural flow or through mechanical pumping. Well, natural flow will provide us with a slower flow, and the infiltration path will usually follow a natural site condition, making it difficult to reach specific layers. As for mechanical pumping, will provide a higher control, but if not done properly, it can lead to the creation of preferential paths. Reinjection also presents the challenge that is many times a single extraction point may require several infiltration points to accommodate the removed volume. So site-specific conditions must be considered, and removed fluids may be reinjected partially and sometimes completely. This will very much depend on the reality we find within the field and the specifics of the contamination. So all these factors lead to high operational complexity, and great care must be taken to avoid unwanted contamination movement. So how can we optimize this reinjection? Well, we use forced reinjection. This helps overcome the hydraulic challenges and supports effective distribution. We utilize low pressure and controlled flow and mimicking in situ chemical oxidation techniques. This avoids compromising soil characteristics. We also use the reinjected fluids to establish recirculation by recovery pumping. This can drive contaminant mobilization and enhance the extraction efficiency. All these principles we can apply in either the vadose or the saturated zone. So what we found out is that reinjection may be enhanced by combining in the fluids to be reinjected biosurfactants or bioremediators. But in this case, the proper distribution of the points, as well as the injection in the correct layers and the correct depths, are key to success. So optimal solutions vary depending on site characteristics. We can apply two different formats. In a permanent format, probes can be driven down to the desired positions on the specific and appropriate layers and can sustain continuous reinjection. Alternatively, a batch system can be applied. In this case, the effluent storage must be implemented to sustain desired intervals. And then periodically, we can mobilize an injection system that can reinject, that can reinject the stored fluid. So putting all these techniques together, we end up with a biostimulated recirculated reinjection. This combines reinjection with biosurfactants and bioremediation and can accelerate contaminant breakdown and improve contaminant mobilization. This is a sustainable remediation strategy and can maximize efficiency. And all these gains can be monitored through direct measurements like parameters as contaminant concentrations. So what are the benefits of this sort of compositions? Well, we can reduce or eliminate effluent transportation, and this will lead to operational gains. It can minimize logistical challenges, reduce the reliance on external treatment facilities, and eliminates risks and emissions associated with effluent transportation. We can achieve lower carbon footprints. This is supported by the substitution of fuel by solar energy and the reduction of the requirements for on-site interventions. Additionally, the use of bioremediation may reduce the requirement for the application of chemicals. Finally, we have significant cost savings. Lower transportation and disposal costs and lower maintenance costs will end up with significant savings. This can be complemented by the reduction of the duration of the project, the better effectiveness of the system will reduce the time of operation that we need to reach our environmental goals. And this will reduce the costs and therefore open up a wider adoption potential. So like I said, lower operational costs, lower fuel consumption, reduced downtime, reduced effluent transportation and disposal costs, and reduced operational time to achieve their environmental goals result in substantial reduction in emissions and operational costs. Specific gains vary depending on site factors, the type of contaminant we have, and where each site is located. But the proposed system can lead to estimated carbon emission reduction of around 40% and operational cost reduction of up to 35%. So in conclusion, the automated BRR system effectively addresses the unique challenges of remote and isolated areas. This is done through the enhancement of operational safety and efficiency through continuous sensor feedback and dynamic adjustments. The incorporation of remediation via reinjection with biosurfactants and bioremediation maximizes environmental benefits. Remote monitoring capabilities allow for centralized control and minimize the need for on-site personnel. And this is a versatile solution that can be adopted in different field conditions and in contexts. It's applicable on a global environment remediation effort and can support sustainable development goals and environmental preservation worldwide. So this is it. I tried to be very brief. If you have any questions, I'm available. Thank you very much.
Thank you, José Eduardo, for your very nice presentation. Please stay with us at the end of the session for some questions. Okay, sure. Now we're going to move to the next presentation. I don't know if finally Dr. Komomo is here. Is not here? Okay, we are going to jump to the next presentation. At the end of the presentation, we are going to try again to talk with Dr. Komomo.